And it all comes down to, ultimately, how cross products work. All right. So, if this is indeed a circle, then ds is always perpendicular to r. Let's fill in the rest of it. So b is the mu naught over 4 pi integral, pull I out, ds cross r over r cubed. Mu naught I over 4 pi. ds cross r are always, they are always perpendicular, as I just said, and so therefore it's just the product of the magnitudes. ds over r squared. Or let me throw in the intermediate step for those who are still waking up. So that becomes rds over r cubed. That gets out with one of those. Now r is constant because it's a circle. So this is mu naught I over 4 pi r squared times the integral of ds. This is just an integral of this, well, of ds, so that would just be the length of the circle. So mu naught I over 4 pi r squared times 2 pi r. Pi's cancel, 2 cancels with 1 and 2 of those, and r cancels with that. And so what I'm left with is mu naught times I over 2r. That's the magnitude of the B field. The direction you can figure out by the right-hand rule. In this particular case, it would be out of the board. So I do want to put in a warning here. I have had students, if I look at the two equations that we have here, we've got the magnetic field from an infinitely long wire, the magnetic field from a circle of wire. Some students, when they get on the test, they're looking at the equations and they see these two equations, you know, without the description here of which one goes with which, and they think circle, 2 pi, and so they take the one with pi to apply it to the circle. Please recognize the pi is associated with a long straight wire. The circle is where the magnetic field is, not the shape of the wire. And pi disappears here. All right, questions to hear?
So we can ignore the direction until the end.
Yeah, and then just think through the end, then think through the direction. All right, let's take it one step further. I got a whole bunch of wire there. Now, if that two-dimensional drawing of a three-dimensional object is kind of not working for you, a solenoid. Solenoid is a ring of wire that you have a current running through it. Usually, at least all my experience with it, is that it's the same current running through the entire solenoid. What is the magnetic field coming out of the middle here? So from a side view, somewhat a side view of it. Now we are going to look at the ideal solenoid. There is a lab where we do try to throw in some reality into it, but right now we're just dealing with ideal solenoid. And so I have current flowing through the solenoid that's either flowing from, if I'm standing over here, either going to be flowing clockwise or counterclockwise, so I do need to define that. So let's just go ahead and assume that it is going around like that. So it's coming out of the board on top and into the board on the bottom. That's the current flow. So if I took this and just did a cross section of it, you'd have wires on top, and you have wires on the bottom that are connected to each other, but it's coming out on top and into the board on the bottom.
So I guess looking at it from that, like straight on, it'd be clockwise.
Yes. And which way, so from this point of view here, which way is the magnetic field flowing? In the middle. Looks like I got a groundswell of 2. Current's flowing around like that. In the middle, the magnetic field's flowing that way. This is my north pole here, and that's my south pole of my electromagnet. So this is, so if I'm looking at it from this point of view here, then well, clockwise like that, so which I believe is what you were saying. So I want to figure out what is the magnetic field in the center. Well, we now have Ampere's rule that we can use, and we know what the magnetic field in the middle is of one loop of wire, and so now let's combine the two. What I'm going to do is I'm going to take a certain number of wires here. I'm going to create what is known as a Gaussian loop. When we dealt with Gauss's law of electricity, we had a Gaussian surface. Gauss's law of magnetism, we didn't do much with it other than just point it out. Gaussian surface. Here, some will refer to it as an Amperian loop as opposed to a Gaussian loop. I will flip back and forth. And inside here, I have N wires. Now, in my drawing, I actually only have 4 wires circled, but we'll make it more generic with N wires. So if I think about the magnetic field created by each of these wires, so I'm going to just take a couple of these wires up on top. Each one has a current coming out. So I have a magnetic field that's flowing in that direction. And this one's got one flowing in that direction, and this one's flowing in that direction. So we have a net magnetic field inside going to the left. And just with this one little small group of wires, we have a net magnetic field going to the left on top, basically outside the solenoid. I think I did just misspeak. I did, before I said inside, did I say it was going to the left? Because, yeah, your right, my left. Sorry, I forgot to reverse it. Going that way. Outside is going that way. But in between, I have a magnetic field going up and a magnetic field going down. My magnetic field between them all cancel out because I got them going in opposite directions. Similar down here. Just looking at 4 wires. The current is flowing into the board, so my magnetic field is flowing around like this from I guess all of our points of view, flowing clockwise around each of those. And again, we get this canceling out in between. On top here, or inside the solenoid, we have a magnetic field going in the exact same direction as it does from up here, and in the opposite direction down here. So it looks like in my solenoid, I have a magnetic field going to the right inside and going to the left on the outside. Classic magnet. However, we have an ideal solenoid here. If I think about, let's just take this one right here. My magnetic field is flowing clockwise. My current's flowing into the board, magnetic field's flowing clockwise, flowing around like this. And I'll do one more. It gets weaker the farther out you go, but it's still there. If I bring in the top one, current is flowing out of the board, so my magnetic field is flowing counterclockwise. Notice what we have. When I'm inside the solenoid, the magnetic field lines are all going in the same direction. But when I'm outside, I've got this conflict here. Purple is going to the left, green is going to the right. So we have a weakening of the magnetic field when we bring both of them into account. And so for the ideal solenoid, my magnetic field outside is 0, and now here it is 0 as well. And there's a lab, the electromagnetic induction lab, where you do a comparison between the ideal and reality. Now, we still haven't found the magnetic field inside the solenoid yet, but we're getting there. We're just setting up. So when we do the Gaussian loop or Amperian loop, we get rid of a bunch of stuff. All right. So now let's take a look at that loop. I've got my square there. I got my current coming out with my in wires. And since my magnetic field is going to the right inside, I'm going to start here, and I'm going to do my Amperian loop in this direction. Because when I'm doing a line integral, I have to follow a line in one way or the other. So I'm going to call this 1, 2, 3, and 4. So Ampere's law, B dot dl is equal to mu naught times I enclosed. And so this is a line integral. In other words, it's B dot dl along line 1 plus along line 2 plus line 3 plus line 4. So B1 dot, well, in essence, delta L1 plus B2 dot delta L2, and then plus B3 dot delta L3 plus B4 dot delta L4. It's going to be equal to mu naught times whatever my current is flowing out or flowing through my loop. Well, what is my current flowing through here? Looking for letters, not looking for a number. So if I have some current I flowing through my wires here, what would be the current flowing enclosed by that loop? let's see, the avoidance of eye contact going on here.
Is it
Thank you
eye-
for not avoiding it.
Is it eye enclosed? Is that one?
I'm looking for I enclosed, you're,
Oh, okay.
are you saying it's I? So it's mu naught times,
Uh,
I know.
DQ or DT?
oh, you're going way fancier than we need to here. You're just doing I. Thank you for progressing this a little bit further. It's actually not I. It's I if we have one wire. But how many wires do we have? It's N times I.
Oh.
Each wire is producing a current coming through this loop. And for those of you who were thinking that, but didn't say it, next time, go for it. All right, so we got this whole bunch of stuff on the left-hand side. We got this little tiny little thing on the right-hand side. Let's simplify this a little bit. Let's do the easy ones here. So inside the solenoid, my magnetic field is going to the right. Outside, there's no magnetic field. So which of these is equal to 0? I got 4 terms here. Which ones are equal to 0? 2 and 4. Why?
Not sure.
Okay. It is indeed 0. But why are 2 and 4 0?
Because those are going in like up and down, and the current's going right, while the magnetic field's going right.
All right. We got 2 explanations. One, we do have the incredible weakening of it because of the going against each other, but more specifically, more generally, exactly what Austin just said. This would be 0 because my magnetic field is perpendicular to my line. So that's 0 for the same reason. We got rid of 2/5 of the problem already. Did we get rid of anything else?
3?
Pardon?
3?
Why?
Because it's moving opposite the direction of magnetic field.
Nope, not for that reason.
Uh,
Remember, ideal solenoid.
Wait, what was your question?
Why, Austin was suggesting that this is equal to 0. This segment out here. And I said, why?
oh, is that part outside the wire?
Yes, it is,
So there's no magnetic field.
and that's why. So there's a simplified down to my magnetic field times whatever my length is there. And so the magnetic field in the center of the solenoid, let's actually come up with a letter here. Let's see, how long is that? Let's make that length, using lowercase l there, let's make this length L, capital L. So BL is equal to mu naught N times I. All right, so these are just a bunch of circles here. We have a circle of wire and a current that's flowing around it. Now, in the case that we did before, it was a complete circle. This one's just slightly off because it starts the next circle, because it's a coil. But B right here is the magnetic field oops, wait, hold on just a second. Oh, okay, sorry, went in the wrong direction there. So my magnetic field in the center of the solenoid is mu naught times the number of wires over I divided by my length L. Remember, this length L here is arbitrary. It just created a loop going around a bunch of wires. So what's really more important is this ratio here, the number of wires per unit length. Off the 0 there. So this is just mu naught times what is known as the coil density times I. So this N coil density, which is just the number of wires per unit length. Questions to hear?
The bunny equation.
Pardon?
The bunny equation.
Yep. And particularly that's now etched in my head. But why not? I have the Joe equation, why not the bunny equation? I guess the Joe, the then, now the bunny.
The pi equation.
Right now, the point.
Everyday English just creeping its way into physics. All right, let's take a small little break here, stretch legs. Come back, so we talked about creation of magnetic fields, now we can talk about the influence of magnetic fields and how they make our lives better. Okay, not yet.
The bottom of the wire, they go clockwise, is that? No,
So the current's flowing around like this in the wire, so it's coming out on top and into on the bottom.
Okay. But I meant like that, yeah, right there, which way are they going?
The current's flowing this way. The magnetic field, that's what the circles are.
Yeah.
The magnetic field is flowing the clockwise on the bottom and counterclockwise on top.
Okay,
Is that sufficient or?
yeah, I see. Yeah,
Okay.
I get it.
All right. I'm gonna pause the camera. Hopefully I'll remember to turn it back on. Maxwell did not name these himself. It came after the fact. He actually had elements of modesty involved. But there is, Maxwell's huge contribution was adding a term to this, which then allowed to derive the speed of electromagnetic wave, which he then did. So there is a missing piece here. We just are not there in terms of development within the class to add that extra piece yet. But Ampere came up with this, but this does bring in the issue of, if I've got a parallel plate capacitor, I have current flowing onto one plate, I have current leaving the plate, but what happens in between? And this is not sufficient to handle that. As well as seems to violate the junction rule. Now I know what you're thinking. Cross products were great, but we don't have enough of them. All right, so let's bring in some more. So the first bit of the class was dealing with how to create a magnetic field, and we hit some specific situations. It's really nice to be able to do the calculus on this one. In 152, it's more of a, hey, here's the situation, here's the equation, and it's frustrating from an instructing point of view of you can't really show how you get there. But let's now talk about the influence of a magnetic field, and more specifically, the force. Well, I guess you could consider this the third physics equation. That the force on is equal to QV cross B. This is the force on a charge. So force on charge Q. Now, as implied in the equation, the charge does need to be moving. There is no magnetic field on a charge that is just sitting there. Well, I should say, if the magnetic field, if I got a magnet and I got a charge and they're both just sitting there, there's no force involved. So this would be the velocity of the charge. And this is the strength of, not the strength of, this is the external magnetic field. So I have some moving charge somewhere else that's creating this magnetic field, and it's having an effect on another separate charge. We will get into, if I've got two currents running, they are both creating magnetic fields that are affecting the moving charges on the other current. We will get there. All right, so let's talk about the directional piece of this. The direction of the force is obviously the same direction as the cross product. So if I have a magnetic field that's coming out of the board, as I generally do in class because it's so much easier than drawing X's. So I have a magnetic field coming out of the board, and I have a proton that is shot into it. Which way is that proton going to be forced when it enters the magnetic field? Well, the velocity is that way. My magnetic field is out. V cross B, the force is up. This is V forced upwards. Matter of fact, looking at it from a point of view of, I think ij and k, so ij in a right-handed coordinate system, k coming out of the board. My proton is moving in the negative I direction, so I have negative I hat. Cross my magnetic field was coming out of the board, so that's k hat. And so I cross k. I cross k is not j. Go back to the I, j, k. It's positive going in this direction, negative going in that direction. I need to repeat it. I cross k is negative j. And then the negative here cancels out with that one. So this becomes negative j hat, which is j hat. Questions to hear? Because we're going to change this slightly. I now send an electron through, going off to the left. Which way will it be forced? So I've got an up and a down. Got two downs, I think. And up, we got two ups and two downs. Three downs.
Down.
Another down. Another down. We seem to be feeling a groundswell over here. Kyle, what do you think? Down. You're going down also, Daniel?
Down.
Whatever.
I mean, down.
Yeah. Let's think about that. The V cross B is indeed upwards. That hasn't changed. But now recognize that we have a charge on Q. Q is negative, so we got an extra negative sign thrown in there. So the electron would be forced downwards. So, because we haven't done enough right-hand rules, let's do one more. Different textbooks will do this slightly differently. I have to go with the way that I remember it. So that's what I'm going to do. Your textbook might do it differently. Whatever you pick, stick with it. Pick one, go with it. Let's go back to the proton. And the Sten gun. The Sten gun technique. Sten gun, automatic, it's a machine, hand-carried machine gun, British commandos. You got the thing you're holding out here and you're shooting like that. World War II. All right, so the bullet comes out the barrel. This is the bullet. You point that in the direction that the charge is flowing, the positive charge is flowing. Magnetic field, generally you don't draw a single magnetic field line, you draw multiple. So this part out here, the part that you're holding on to, this is the magnetic field. The thing that forces a gun to fire is the hammer, the thing that's sticking up right here. That's the direction of force. So I have the direction of the particle, direction of the magnetic field coming out, thumb points in the direction of the force. So a proton will be forced upwards. If my magnetic field is going into the board instead, and I shoot the proton in like that, I got my proton that way, the magnetic field that way, the force is down. For negative charges, it's the opposite. So if this is an electron, remember that positive charge flow and negative charge flow are just opposite directions. So if I have a negative charge going that way, I'm pointing my finger opposite. Magnetic field coming out, thumb points down. The electron's going to be forced downwards. Or you could just go to cross products and do an I cross J kind of thing. Let's do some numbers. Ooh, actually, before we do numbers, one more thing. So let's go back to the proton. It enters and it's going to be forced upwards. So what is the path of the proton going to be once it starts getting forced upwards? Potentially, I wasn't quite sure what your hand gesture was, Lawson.
Diagonal.
Okay, so it'll start to move. So now it's moving this way. Which way will it be forced now?
Oh, let's see.
It actually depends on how wide it is. We have basically the force. The force is perpendicular to V and B. If the force is perpendicular to the velocity, what kind of force is that? Flashback to the first semester course. Absolutely. We have a centrifugal force. We're not changing the velocity of it, all we're doing is changing the direction. Now recognize how powerful this is. Well, let's go through let's assume that V and B are perpendicular to each other automatically. So my magnitude of my force is just equal to QVV. It's a centrifugal force, so that's going to be equal to mv squared over r. That cancels out with one of those speeds. So the radius of curvature is equal to mv over qv.